Recording is rolling. Welcome to Wednesday, April 20th. So here's what we do today. I'm gonna do real as condensed as I can recap of Unit 7, which is a pretty hefty topic. You guys remember because we're talking about rotational dynamics. So everything you guys learned in linear, here guys pay attention here, had some rotational analog to it. So yeah, give you guys that. Right, and then I've got a 7-point FRQ lineup for you guys. The time worked out in my last AP class. So yeah, so pay close attention to this synopsis I'm going to give you guys on rotation stuff because it will be directly helpful for actually not only this FRQ you're going to get here in a few minutes, but also a lot of your quiz questions. You guys got that quiz going on. You guys remember some upcoming due dates? So yeah, you guys have these in your planner, right? There's AP Classroom due this coming Monday, and then yeah, thank you. That review quiz that's out the Monday after. Give me a second. All right, let's look at. So we start with. Yeah, go ahead. Great. Get my notes straight here. Rotational kinematics. So. Yeah, split notes here. There we go. All right, so what was going on in linear motion versus what's the rotational analog? Okay. All right, so let's start with some kinematic stuff. So in linear, you might be interested in how far is something moved in meters, how fast is something moving meters per second, like linear speed, linear velocity, or how about acceleration? If something's speeding up or slowing down, meters per second squared, right? Now, and then time was still time, so in seconds. Okay. Now, rotational, I'm more interested in. Ooh, look at this turntable, right? Ooh, right. Not how far something moved in meters, but how far is that turntable rotated? I'll call it theta. And you can measure that in degrees or revolutions, but the best way is to measure how? Radians. And the reason that's the best way is because you can plug these numbers directly into equations, which I'm working towards. But before I get there, not how fast something moving meters per second, but how fast is it rotating? That's angular velocity, radians per second. And then instead of meters per second squared, you could have alpha, that's angular acceleration, radians per second squared. That's like if that turntable was speeding up spinning or slowing down spinning. I think right. Now you can connect these two because, like, for example, break out this turntable again. You guys see this dot on this turntable? Okay. If I give this thing a spin, or how about even better? Kind of looking at different locations. So I got one near the middle, and then one kind of here, and then on this dot, maybe I'll go this pick. Right? Watch these picks go around. Oh, it looks like the further out it is, like the further distance it goes, like meters, and also the faster it's going meters per second if you aim a radar gun at it, right? Okay, so what I'm trying to get at is that there is a connection between variables on the left side and the right side, and it goes through radial size. You guys remember how far something gone is equal to theta times r? How fast is it moving is omega times r, and tangential acceleration, not centripetal acceleration, that's a different thing, but tangential acceleration is alpha times r. Okay. And that is where r is the radial distance. So like that pick that was right in the middle had 0 radial distance from the center, so it wasn't going anywhere. Right? But the further out, the more magnified those were. Yeah, you guys remember this poster right here? You guys remember this one? Right? And you know what goes hand in hand with rotational kinematic, because we're talking about rotational kinematics, right? I haven't brought in forces or torques or masses or rotational inertias yet. Right? Are these. So we're still on rotational kinematics. You guys remember those 3 classic equations going back to some of the first stuff you learned, like Unit 1. But instead of x equals v naught t plus half at squared, now it's theta equals omega naught t plus half alpha t squared. It just plug in the rotational analogs and you get 3 perfectly valid rotational kinematic forms. You guys remember those? Right? Okay. Now let's move on to some dynamic type stuff. Because in linear, you guys remember mass was measured in kilograms? Okay. What's sort of the rotational analog to mass? It's rotational inertia, right? Which remember is for a single point here, well, I'll say this: the sum of them are squared. Okay, you guys remember, and that would be in a here kilogram meter squared. So some number of kilogram meter squared. Okay. For a single point, it would be mr squared, and then the sigma means if you have multiple points. How about this? You guys remember a couple of meter sticks, and it had weights taped to them. So there was one set of weights near the center, one set of weights far out. These both weigh the same mass, same weight, right? But then if you grab them in the middle, here's like a hand holding the middle, okay, and you start shaking back and forth, like rotating about that central point. One of these very easy to change its state of motion, and one of these very hard. Which one's very easy to change its state of motion? The top one. And if it's very easy to change its state of motion, that means it doesn't have very much inertia, but in a rotational sense. Not very much of this. Because the sum of them are squared. It's like most mass would just be in the taped on masses, right? M times little r squared plus m times little r squared. That'd be a very small number of kilogram meter squared for the top one. But the bottom one, that huge radial size that's getting squared, oh boy, that's like a huge rotational inertia. Really hard to change the state of motion, that one. Hey, guess what? Then there was, how about this? Sort of an analog to force was like a torque. You guys remember, instead of force measured in newtons, there's like a torque measured in Newton meters. Okay. I'm kind of running out of paper here, but here, since I'm talking about torque though, okay, if there's a force, there's going to be an acceleration. If there's a torque, there's going to be an angular acceleration. Okay. So what is how about this? You guys remember torque is equal to R cross F? You guys remember that? And let me break out my poster on that one, because here's a really good visual. Yeah, you guys remember this? Okay. So it's this radial size times this force causes some turning moment, but you need to keep in mind it's only the perpendicular component actually causes any rotation. You guys remember that? So playing off this angle theta, it'd be sine theta, but you have to be careful because they could totally throw you a curveball and put in this angle, in which case it wouldn't be sine, it would be cosine, wouldn't it? If they swap and put in the wrong angle, right? You guys following here? Yeah. I'm totally giving you guys points. I could totally pop up on the AP example, right? Right. So, yeah, just the perpendicular components that you multiply together, that's R of sine theta. And look, it actually causes an angular acceleration. Like, for example, if you have, say, a disk that's free to rotate about the center, and you wrap a string around it, string, okay, and then you pull with some tension force tension. Well, if you multiply that by this radial size r, and these would be at right angles to each other for this type setup, right? R cross F, wouldn't that give you some torque? And as long as you're providing a constant torque, this thing doesn't spin at a constant rate. It picks up at a constant rate, right? It has a constant angular acceleration. So torque is also equal to I times alpha, where remember I has something to do with like the rotational inertia of this disk, right? That is analogous to F equals ma. Look at that. Instead of force, now it's a torque. Instead of mass, now it's rotational inertia. Instead of linear acceleration, now it's angular acceleration, right? Guys remember that? Right, now, we can have another poster in here for you guys. Yeah. I did sort of skip over one of these posters. Right. Backtrack a little bit to this I. You guys remember I is like the sum of mr squared, right? Which represents inertia in an angular sense. It's on its rotational inertia, right? So here's rotational inertia table. Every physics textbook has one of these. For AP, they don't expect you to memorize any of these. If they wanted you to apply any of these, they would give it to you. A classic example is just a cylinder rolling about its central axis like this. Look at the cylinder rolling. Now, if this is approximately a solid cylinder, there's an mr squared for each of like a billion points on this thing. But a lot of the points are not actually at the full radial size. So the overall effect has to be less than mr squared. And it is, it's 1/2 mr squared. A ring, of course, would be mr squared because every single point is equidistant from the center. So mr squared, the aggregate effect is mr squared, right? Okay. Here's a bowling ball, here's a basketball, here's other things that could roll or rotate about some axis, right? So just be aware that this does exist. These would be in kilogram meter squared. The solid cylinder is a real classic one, right? That's if I had to like put money on any rolly thing you got, it'd probably be this one. Okay. Right. Then I put continuing on this table that again kind of ran out of space for. I need to talk about momentum because I haven't talked about momentum yet. You guys remember there's a rotational analog to momentum? So that's going to go something like here. Instead of linear momentum is mass times velocity. Isn't angular momentum equal to I times omega, right? Just pop in the rotational analog parts, right? Is that true? And what if momentum is changing? What's that called? It starts with an I. Impulse. Yeah, impulse. You guys remember change in momentum, impulse? That could be mass times change in velocity. That's what it usually is. But it comes from where? It's from applying a what for a what? Yeah, force for some time interval. In fact, you guys are going to get a graph that's force versus time, and the area under that curve represents the change in momentum, right? You're going to see that, right? But what's the rotational analog to that? Yeah, torque times time, right? So an angular impulse is I times change in omega. You get by applying a torque for some time interval. You know what? That also would be a great story to. This equation would fit this story, right? Wouldn't it? If you apply R cross F, there's a torque. If you apply that for some time, that would result in some change in angular momentum, wouldn't it? Right? Is that true? How about this? How about this though? Oh, here, hold on. Actually, let me flash up these graphs before I forget, because you're going to see, almost guaranteed, you're going to see each of these graphs on the AP exam, right? And we sort of just did this. So if you apply a torque for some time, well, if you throw it on a graph, wouldn't the area under that curve represent the change in angular momentum, right? And it'll probably be a rectangle. Well, it doesn't have to be, but good chance it will be like a constant torque, right? And about half you guys are in calculus, and you know that, well, if you can integrate, you can also work backwards. That would be the derivative. And that's like the graph on the left. So if you have angular momentum versus time, then the slope of that graph would represent the torque. Okay, so these two graphs are like two sides of the same coin, right? And again, if you're in calculus, one is the integral, the other is the derivative, the other, right? Okay, you guys got that? All right, so I want to mention a couple things about angular momentum, though, or momentum and angular momentum. So continuing on this part of the story. Okay. Do you guys remember? Now, here's one you have to memorize, because a lot of these equations are on your AP equation bank, but the next one I'm going to do is not. What is the angular momentum of a single point mass? Now, this one you have to memorize. So who has this one memorized? Who knows what is angular momentum of a single point mass? Close. Start out with regular momentum, mv, and then multiply by r, mvr. Okay, guys, see this right here, right? Almost for certain, you're going to get a pretty good chance, I should say. You're going to get a question on this on the AP exam, and this is not on your AP equation bank, so you have to memorize this one, right? Right. So angular momentum of a point. What do we mean by a point mass? Like, for example, what if you have like a swivel stick? It might be vertical, it might be horizontal, and you have like some ball of clay that's like flying in its own mass and its own radial size r, right? It of course, it's flying at some speed, so we label like a v, like velocity, right? With mass times velocity would just be the pure like linear momentum. But then if you multiply it by this radial size from this pivot point, wouldn't that represent this right here? You guys see that? Right. And one last thing. How about this? This pen has some mass. I drop it, goes clunk, goes smack on the paper. What if instead this pen, same mass, went ba-boing? Which would impart more force onto the surface? Flying stick or ba-boing? The ba-boing does. And the reason is, here, if you go back and read the music of this equation, right? So the pen has some mass, m, right? Change of velocity. Let's say it's like landing at 5 meters per second. 5 to 0, like inelastic. Well, that's a change like 5. But if it bounces back 5 to -4, guess what's the difference between +5 and -4? 9. Ooh, that's almost twice the impulse, isn't it? Thank you. Right, you guys see that? Right. So by bouncing off, you can get a lot more force imparted, a lot more change in momentum. And okay, great. You guys see that? And you can do a similar thing with the analog, right? So the analog situation for rotational. So like, what if this ball of clay collecting sticks? Or what if it's a bouncy ball that goes boing and bounces off? Hey, what would get this rotating faster? Ooh, you know what? That is actually sort of leading into this FRQ I'm about to give you guys. So yeah, let's switch over and I'm about to get you guys this FRQ.